Now that we know how to put our ordinary differential equations into state space form, we now want to be able to use MATLAB to solve for our dependent variables. So to solve for the dependent variables as functions of time, or really at discrete time points for this, we want to use the numerical solver in MATLAB. And most of the numerical solvers in MATLAB, there's a couple to choose from, or if you use a numerical software in some other package that's not MATLAB, most of them use a Runge Kutta method for solving our ordinary differential equations. There are other methods that some employ, but Runge Kutta is the most popular. I won't get into the details of how Runge Kutta works, but you can look it up to see how is it actually finding our dependent variables. So the way we're going to use MATLAB to solve these is using most of the time using the ODE45 command to solve it, and it is a little bit complicated how it works. So I'll try to go through it here. So ignore the left-hand side right now, but the right-hand side we use ODE45, and we want to tell it to use t and y. So in this case, t is going to be our independent variable, usually time, and I'm using here y, but you could call it x or whatever you want. That is our state, our vector of state variables. In the previous examples, we just had an x1 and an x2, but we could have x1, 2, 3, 4, 5, etc. In the way I'm writing it here, y is that vector. And then some function, I'm just generically right now calling it myfun, that takes t and y, and then maybe some other arguments as well. But most importantly, the order here, it's going to take the independent variable t, and then the second is the dependent variables, which are the state variables y. And then it can also take other parameters that we'll get into. The second argument that ODE45 takes then is going to be the time span we want to solve for. So at what time do we want to begin this numerical solution? And at what time do we want to end the numerical solution? The third argument that ODE45 takes is going to be our initial conditions. So this is going to be what are the initial conditions on our state variables. When we were solving this by hand, we saw, for example, we were told what x of 0 and what x dot of 0 was. We have to make sure that when we make our map from our original variables to the state variables, we realize how those initial conditions also map over. So again, if we had state variables of x1 and x2, if x1 is equal to what we originally called x, we have to put the original value of x1 in, followed by the original value for x2, which would be whatever our initial condition was on, say, x dot. And then the fourth argument is different options that we can feed ODE45 to change the tolerance settings or some other things about it, and we'll get into that a little bit later. But the crucial things here are going to be the first argument we give it, which is what function we're going to be using. The second is the time span we're going to be evaluating at, and the third is going to be our initial conditions. So a little bit more on this, when I'm in this example just calling myfun. This function, all its purpose is to assemble the state variables, or more specifically, it has to assign right-hand values to x1 dot, x2 dot, etc. So the only job of myfun is to output the values of the derivatives of our state variables. And this will be more clear in the example how we assemble this function we call myfun. And lastly, we want to look at the outputs to ODE45, what's actually on the left-hand side. So what I'm calling t and what I'm calling capital Y here. T is going to be the timestamps of our solutions. Often when we use ODE45, we just give it a start point and end point to start evaluating time, and it's going to make its best judgment of where in between to also be sampling these times. It's not necessarily going to be uniform between the start point and the end point. By default, ODE45 makes the decision of where it's going to do it. Now there are advanced options where you can specify where you want it done, but for right now we'll just let the defaults work itself. So t is a vector of all the timestamps it's evaluated our state variables. And y is generally going to be a matrix output. Y is going to have as many rows as t, and as many columns as we have state variables. And this is where we have to pay attention to what our state variables were. The columns of y each are going to be one of our state variables. So the first column is whatever we called x1, the second column is whatever we called x2, third column, etc., until we have all of our state variables. So each column is a state variable, and then each row corresponds to the timestamp in t. So what is the value? So the first row might be what are the values of x1, x2, x3 at time is 0. The second row might be the values of x1, 2, 3 at time is 1.2 seconds, etc., until we have all of those timestamps complete.